Hello everybody and welcome back to Chem Talk, where today we'll be talking about the kinetic molecular theory of gases. Personally, this is one of my favorite lessons just because after you learn all these different gas laws like Charles, Boyle's, and the ideal gas law, you're kind of wondering to yourself, how do they all fit in together and why is it so important that I know all of them? Well, the kinetic molecular theory allows you to kind of understand how they all fit in with each other. Now, what is the kinetic molecular theory of gases? Well, this is a model that helps chemists understand the physical properties of gases on a molecular level. So we're going to go into a couple of principles and a couple of assumptions that you should know in order to understand the molecular theory of gases. Now on the screen right here, we're going to have an image, so I want you guys to keep this image in mind when learning about this theory. Visualizing it this way helps you comprehend how the gas particles are moving as a whole. We're going to move on to our 5 assumptions that the kinetic molecular theory has. So the first assumption is the volume of gas particles themselves are negligible. So when you're finding the total volume inside of a container, you only find the volume of inside the container itself. You don't find the volume of the gases because it's so small that it does not matter towards the total volume. So the volume, because the particles are so small, it does not matter at all. The second assumption that we have is gas particles exert no attractive forces to each other or their surroundings. So they're moving so fast that they don't have the opportunity to be attracted to anything, which I find really cool because then they're kind of, on their own, and unless they hit each other a certain way, they're not really doing any collisions or reactions with each other. The third assumption that we have is gas particles are always in a constant state of motion. They move in straight lines until they collide with something else, and that moves them on into another direction in a straight line. So they're always in a state of random motion, and in this picture over here we see that this particle, for instance, hits a corner of the object, then it hits another corner and it changes the trajectory. Then it hits something else, it changes the trajectory, but how it changes trajectory and how it changes the direction is completely random. And where it hits is also completely random. The fourth assumption that we have is collisions of gas particles is completely elastic. So the energy inside of a gas particle after it hits something is the same as before it had the collision. So there's no energy transfer whatsoever, so that means it keeps all of its kinetic energy. The fifth and last assumption that we have is the average kinetic energy is directly proportional to the absolute temperature. So when the absolute temperature equals 0, that means that there is no motion in these gas particles. So over here I've tried to illustrate that at a higher temperature, your gas particle is moving a lot faster. And at a lower temperature, your gas particle is moving a little bit slower because the higher temperature there is, the more motion there is, and the more volume that the particle can take up. We're going to move on to the application of the kinetic molecular theory. So one of the laws that I want to bring to attention is Charles' law, which states that V1 over T1 equals V2 over T2. And this applies to the fifth assumption that we just went over, where the higher the temperature is, the more the particles hit the edges of the container. So that increases the volume. So they're both directly proportional to each other. So the higher temperature equals a higher volume. And this can actually be seen in a real-life application. So say you're holding a balloon when it's cold outside, you might be snowing or something like that. Your balloon's going to be shriveled, it's going to be deflated, it's going to look very sad. And when you're outside on a hot summer day at a carnival or something like that, and you have a balloon, it's fully inflated. Now, let's try to imagine that it's on the same day, right? So, or, you're going from a cold outside to a very warm inside. What's going to happen is when you're outside, this gas particles are going to slow down because there's not a lot of temperature. And the temperature is actually slowing down the motion of these gas particles. And as the air around it gets warmer, as the temperature increases, the motion increases and it becomes a lot faster, which is why it takes up more volume. It's hitting the edges of the balloon a lot more.